This is a lab problem from section 4.1. It says here to find the critical point of the function, and the function is given by g of y is equal to y minus 2 in the numerator and y squared minus 2y plus 4 in the denominator. So what we want to do first is to take the derivative, and the derivative of this guy is going to be a quotient rule. So let's find the derivative. The derivative is a quotient rule. We're going to be taking the low. I think of it as low d high minus high d low. So low is y squared. I'll put parentheses around just so we're clear about the products that we're doing. So that's a y squared minus 2y plus 4. And then times the derivative of the numerator, which is 1. And then the minus high to low, so that's the high is y minus 2. And then the derivative of low is going to be 2y minus 2. And then divided by low squared, which is basically this whole term, the y squared minus 2y plus 4. That whole thing squared, and that should be it. You can you're more than welcome to simplify this, and I think it would be beneficial if we actually do simplify it, but we can do that in the next step if we want, or they did it for us. But you know, you're not going to get these things in your regular homework assignment. You have to actually simplify yourselves. So this is our simplified version. We got negative y parentheses y minus 4 all in the numerator divided by that y squared minus 2y plus 4 quantity squared. So step 2, the critical numbers occur when the derivative is equal to 0 or when the derivative is undefined. So we have to consider both of those scenarios. G prime of y is undefined when the denominator, that's the quadratic, y squared minus 2y plus 4 is equal to 0. So gy prime is undefined for the following values. Let's take a look at g of y. If we try to factor this, or we use a quadratic formula to try to factor it, so we're focused on this quadratic. We're going to take a look at when y squared minus 2y plus 4 is equal to 0. So the quadratic formula says we have y equals, and then we're going to want a fraction. So let me set up a fraction first, and then I'll fill in the fractions. So this is going to be negative b, which is negative 2. And then we have a plus or minus the square root of b squared. So that's negative 2 squared minus 4 times a times c, where a is equal to 1 and c is equal to 4, all divided by 2a. So if we pause here for a moment and take a look at this, we have 4 in here. Well, let's actually rewrite this down here and then make our changes. This is going to be equal to 4, and then this is going to be equal to 16, and we have 4 minus 16. That's going to be negative, and so in this particular scenario, we're going to have no real roots. So if we have no real roots, we can say that this thing is not going to have any places where the derivative is not, it's undefined, and that's when the denominator is equal to 0. So we don't have any of those cases, so we'll put DNE here. Does not exist. All right, so no real roots. This is for the denominator. And now there are no real roots for the denominator, and g prime exists for all real numbers. So that means the critical values are only going to happen when the derivative is equal to 0. And the derivative is equal to 0 when the numerator is equal to 0. And so the critical numbers are as follows. We're going to set this equal to 0. This is simple enough to figure out. We have y is equal to 0 and y is equal to 4. So we just have two critical points, and that's going to be at 0 and at 4. Okay, so I think for this problem, that's all they're looking for. I think it might be worthwhile to take a look at the graph of this function that we just studied. And if we take a look at it, we see that it's kind of flat the way it looks right now. So I graphed it on Desmos, and then this is how it looks like. It looks like these values are pretty small, 0.5, and then we got some high values over here. So it might be worth zooming in, maybe go up to maybe from -1 to +1. That might not even be good enough, but let's take a look. Let's get our y going from -1 to +1, just so we can have it a little bit exaggerated. And here it's kind of clear what's happening. We have a local minimum here. That's a slope of 0, a tangent line slope of 0. We see a place here where it hits the x-axis, but at this point that's not really much of a concern for us, although you can see that's when the numerator is equal to 0, the original function at 2. And then our high point happens over here when x is equal to 4. So the result that we got, our critical values, are happening at 0 and at 4. So that's a good confirmation.